So now we're going to go on to the part of the syllabus that considers the factors that affect equilibrium. And so this is going to cover the concepts of explaining and predicting the effects of temperature change on chemical systems at equilibrium by considering the enthalpy change for the forward and reverse reactions, explaining the effects of changes of concentration and pressure on chemical systems at equilibrium by applying collision theory to the forward and reverse reactions, and applying Le Chatelier's principle to predict the effect changes of temperature, concentration of chemicals, pressure, and the addition of catalysts have on the position of equilibrium and on the value of the equilibrium constant. So the main factors which affect equilibrium and affect the position of equilibrium will be temperature, concentration, which is relevant for liquids only, and pressure, which is relevant for gases only. And so concentration and pressure are very closely tied together. They have basically the exact same effect, except concentration will be relevant for liquids, whilst pressure will be relevant for gases. So to understand these processes, we need to have an understanding of what Le Chatelier's principle is. And so this is understanding how reactions will change when different conditions are going to be applied. So if a system is subject to a change, then the system will act to partially oppose the change when that change occurs. And this is because the system wants to reattain equilibrium. So when we're looking at collision theory, for a reaction to occur, the particles must collide in the correct orientation and have enough energy, so being at or above the activation energy, in order for products to be formed. So at a low concentration, there's going to be less reactant particles moving around, so it's going to be less likely that they will collide and form a viable product. Whereas at a higher concentration, there's going to be more collisions because there's more reactant particles moving around, and so it's going to be more likely that the collisions between them will be viable and at or above the activation energy, and it's just going to be more likely in general that the particles will collide because they're in a smaller space. So when we consider how temperature affects the equilibrium position, we can consider how temperature affects the movement of particles in a system. So temperature increases the energy of the particles in a system. So we remember when we consider the kinetic theory tells us that when the particles have more energy, they're going to be more likely to collide, and hence they're more likely to be at or above the activation energy when they collide, and so will be more likely to form products. And so if particles have a higher energy, we can say that they're going to be more likely to overcome the activation energy. And so the particles are more likely to overcome the activation energy for two main reasons. And this is because the particles carry more energy, and so a single collision will be more likely to cause a reaction. And then the collisions are going to be more likely because the particles are moving around more, and so if they're all moving around more and all frantically moving in this one container, then they're going to be more likely to collide and hence form the product. And so this is going to have the most impact on the reaction direction because it requires more energy to overcome than the activation energy barrier. So this means that in any given system, increasing the temperature will shift the position of equilibrium in order to favor the endothermic reaction. And so this is because the system wants to decrease the temperature back to normal in accordance with Le Chatelier's principle. Now, when we consider concentration and pressure, concentration, we remember, is for liquids, whilst pressure is going to be for gases. And so these are both going to work in the exact same way, in the way in which they affect equilibrium for various different systems. And so this is that more molecules are going to be present in space. So obviously, if we've got more present molecules, they're going to be more likely to collide, and thus the amount of reactions is going to be increased because it's going to be more likely that those particles can collide at or above the activation energy in order to provide a viable product yield. And so this is going to favor the reaction that consumes the most reactant to produce the smallest amount of product, so considered in moles. So if we are to increase the concentration, we're going to favor of the reactants, we're going to favor the forward reaction. Whereas if we increase the concentration of the products, we're going to favor the reverse reaction, because we want to use up all the product which we've put into the system. Whereas if we were to take out product from the system, we would favor the forward reaction because we want to replace the product which is being removed from the system. Whilst conversely, if we were to take reactant out of the system, we would favor the reverse reaction to produce more reactant because we want to replace the reactant which is being lost from the system. When we consider pressure though, we want to consider which side of the reaction has the most moles of gas. So if we increase the pressure, it's the same as increasing the concentration, but for a gas. And so we're basically shrinking down the size of the container, so it wants to occupy the least amount of space as possible because there's not enough room for all the gas particles to move around. So we want to then favor the side of the reaction with the least moles of gas, and so we'll produce the most of that. Then on the flip side, if we're to decrease the pressure, that's the same as decreasing the concentration and making the container bigger. So there's more space which the gases can then occupy, and so they want to produce the most moles of gas, so in order to occupy all of that space, and so they will favor the side of the reaction which has the most moles of gas. And then another important thing to consider with pressure is that if both sides of the reaction have the same number of moles of gas, then there's going to be no effect of pressure on the position or movement of equilibrium, and so the system will just remain at equilibrium when that occurs, because it can't favor either side of the reaction if they both have the same number of moles of gas.